Hi everyone, I'm Jeff Siegel and I'm going to talk about a project where we measured particle concentrations in 20 homes with low-cost optical particle counters. I'll begin by acknowledging my co-authors who did a lot of this, collected a lot of this data, as well as did some of the machine learning that I'll talk about at the end. So we all know that exposure to particulate matter is important from a health perspective. It's probably the single most important indoor pollutant category. We also know that filters are one way to reduce exposure to particles. And so with that as a motivation in mind, as part of a bigger project studying filtration, we deployed low-cost optical particle counters. You can see them there in the picture in 21 homes in Toronto. The site sample is actually 20 site years of data. We had one site that had a plumbing issue that had to be replaced partway through the study. And over the course of the year, we deployed 4 different levels of filters, MERV 8, and then MERV 8, 11, and 14 electret filters. And if you're familiar with MERV, it's from ASHRAE standard 52.2. So each of those homes in a random order got all 4 of those filters installed for 3 months. And as part of this project, we measured a lot of data, most of which I'm not going to talk about, except for the one piece I am going to talk about is we looked at how often the central forced air systems operated in each of these homes. And then we used this low-cost monitor that, because of data storage limitations, we collected the concentrations every hour on the hour for a minute. And the counter has 2 bins, greater than 0.5 and greater than 2.5 microns in diameter. So the first thing I want to show you is just what the overall concentrations looked like across our homes. This is the concentration first on the left relative to the month of January. And we did that normalization for reasons that will become clear in a second. And you can see in most Toronto homes, you see a particle concentration. There's a lot of variation across our sites, but in general, we seem to see somewhat of a peak in the late summer, early fall. You see a very similar trend in outdoor air, and the outdoor measurements were taken at a central monitoring station, and that's why we chose to normalize to January, so we wouldn't have any monitor differences or so on impacting these data. And you can see that they follow a very similar pattern in general. One of the things that's important when you're looking at indoor data is to be able to know when indoor sources are important, because they can affect things relative to outdoor sources. So we developed a source detection algorithm for our data. It's a relatively straightforward algorithm. It looks at evidence of an elevation of concentration. It looks for a slope upwards, and it looks for a decay after a peak in a source. And if those things are all triggered, then it says the source is active. And it's quite a crude algorithm, and we see relatively consistent results, somewhere between about 40 and 55% or so of the time there are indoor sources active at these sites. Just a comment on sources while we're talking about it. This is one of the more interesting samples in the study. This is the median concentration. We've converted it to an approximate PM 2.5 concentration in one of the sites in the study, and the typical sites were below 10 micrograms per cubic meter almost all the time. So this is really a aberration, and it happened every night. So starting at midnight, the concentration would start to go up. At about 3 or 4 a.m., it would start to decline. And this is the median concentration over the course of the year, so this is really quite a typical pattern. And I'll make a long story short, and the source here was an essential oil diffuser, which the occupant of this home used for both the humidification benefit as well as the essential oil benefit. And they are huge particle generators, just absolutely massive. And that's a good example of how we wouldn't have seen this unless we were doing, this type of continuous monitoring with the low-cost monitor. So what we were really interested in this investigation was filter effectiveness or filter performance, and we assessed that here with a common metric called effectiveness, given the symbol H. And the effectiveness we're defining here is kind of a relative effectiveness, where we define the effectiveness as the concentration with whatever filter we're talking about relative to the lowest performing or lowest efficient filter in our study, in this case a MERV 8 filter. And so the idea here is we can get what's the particle concentration in these homes when there is a more efficient filter installed, and theoretically that should be lower, and therefore we should see an effectiveness that is relatively high. And the actual answer is a lot more complicated than that. So this shows each of the sites with the filters installed. The different filters are indicated by different color bars. And one of the first striking things about this picture is about half of our data points are showing a negative effectiveness. That doesn't mean that the filter is generating particles, but what it does mean is that the concentration is higher with the other filters than it was with the MERV 8 filter, which is nominally less efficient. And so that's one interesting thing. The other thing here is there's definitely not a pattern with filter performance. That is, the higher efficiency filter, the MERV 14 filter, does not by any stretch of the imagination perform consistently better than the other filters. So it's kind of suggesting that filtration performance is not so simple. And one of the big factors is how often the fans run, and I'll come back to that point a little bit later. But fundamentally, the fans didn't run that much. Our median run time, how often the fans ran in these systems, was a little under 10%. And so that's because it was a relatively mild year, and we're in a heating-dominated climate, so most of the runtime in Toronto comes during the heating season. And so if you have both a mild winter, and we also happen to have a mild summer that year, there was not that much operation of the forced air systems. Although that's less than a factor of 2 smaller than the typical North American home. So it's not a huge impact here. Our sample was dominated. These were all homes in downtown Toronto, which is an older building stock in general. And so, the buildings were relatively leaky. So we would expect filtration to have less of effectiveness because particles are already being removed by ventilation. And one of the things we're a little bit worried about is, were there different sources present with the different filters? And that's definitely a possibility if indoor sources are important, as they were in many of our homes. So we calculated that effective metric again, but this time we only considered the period of time when sources were not at all active. And so we got rid of close to half of our data in most of these homes because that's when our source detection algorithm said a source was active. So really we are trying to compare non-source affected periods just to be sure that that wasn't an issue. And the data get a little bit better, but you still see the same sort of pattern. About half of our bars are below below 0, indicating that the concentration was higher. So this really suggests that in these homes, the level of filtration didn't make much of a difference. And that's backed up by the other things we did in the study. This shows all of our data put together. This also shows both particle size bins that the optical particle counter have. And you can see, again, a wide range of effectiveness across all our sites for the different filters. But you can see the medians are, generally speaking, between about -10 and +10. So very small average impact of filters in these homes. And again, that's consistent with other things that we measured. To put a little bit more spin on some of those other things, the upper picture here shows the in situ efficiency for one of the sites in the study, and the different colors are for the different filters, and the lines that you can see, the thin lines, show the efficiency of the filter as measured in a standard test. And what we see in this site, and in fact in most of our sites, is that the efficiency installed is slower than the standardized test efficiency. That has to do with bypass as well as phase velocity and some other issues. And so our installed efficiency is lower. The lower picture shows some modeling work we did on runtime in a separate investigation. And basically what this shows is that even if you have a very efficient filter, And if you have low runtime, you just don't see that much effectiveness from the filter, just simply because air isn't going through it. So that runtime is a critical piece of the puzzle as well. So we have all of this data. What else can we do? And so we tried a bunch of both supervised and unsupervised machine learning models to see if we could predict these particle concentrations based on, for example, household factors. And we tried a lot of different things, and the short answer is we couldn't do that. We were not able to get a model that offered a lot of explanatory potential based on the building factors. Now, I think why that is in this sample is that these homes are not that different from each other. Mostly older homes, mostly leaky homes, mostly low runtime. And so, you know, we just don't see much predictive ability at all. But we also tried an unsupervised learning model, and the question that model looked at is, could it predict elevated periods of concentration? And the figure on the left shows one example of that for one of our sites. And every time you see a red dot there, the unsupervised model is saying, hey, the concentration is elevated for this site. And that's a really kind of interesting thing because it, of course, identifies elevated particles differently at every site based on their typical patterns. And that's kind of cool, and you can see that visually it makes sense. So some of our homes had just a few points. I think this one was the one with the most, where you see you know, some number close to 100 elevated hours over the course of the year. And so what we did with that data is we said, well, can we predict those ahead of time based on the previous couple of hours of particle concentration? And that's what the two confusion matrices show. And so just these take a little bit of explanation. So the zero condition means that it's blue in the figure. So the particle concentrations are not elevated. And the 1 means that they are elevated. And then what's along the bottom here is whether the algorithm predicts that right based on the 2 previous hours of concentrations. And it kind of depends a little bit how you set your parameters and what you care about. And so the first model is kind of the best performance we could get out of a model for one of the sites that had about 30 elevated periods. And what you see here is that we were able to do pretty well. We were able to predict over half of those elevated periods. And we had both some false negatives and some false positives. We then looked at things a little bit differently, and that's with a slightly different model, a little bit more stringent, that allowed more false positives into the mix. And you can see that, you know, we only had 7 false positives before, and we have, if you look in the upper right, we have over 200 false positives. But we get, this time we get about 90% of the actual elevated periods predicted ahead of time by the model. So why were we interested in this? Well, we're thinking about the application of, you know, for instance, let's say you had some type of control parameter that was measuring the concentrations in the house and said, oh, we're likely to have an elevated period soon. Why don't we turn on the fan if it's a central system, or you could imagine this for a portable air cleaner too, and ahead of time predict, you know, get rid of those elevated concentrations before they occur. And we were able to make this model work pretty successfully with about a month of hourly data ahead of time. And so I think it offers an interesting way of looking at low-cost sensor data for control purposes. So in conclusion, high-efficiency filters, you know, definitely do not necessarily have high effectiveness. It depends a lot on use case parameters, and we saw a lot of variation. We saw, you know, no evidence that filters can reduce indoor PM in this sample of homes. But where I think low-cost monitors get really interesting for us, in addition to kind of answering research questions like those ones above, is, you know, can we start using those in predictive models and start using them for alternative control approaches or exposure avoidance approaches? Thanks very much, and I'll acknowledge the funders for the work, ASHRAE and NSERC, And if you want to see more details on this data set, there's a paper that's published in the ASHRAE Science and Technology for the Built Environment Journal.